Assalamualaikum and very good morning class. Our next topics are exponential Fourier series and time shift. Before we proceed with exponential Fourier series, let us recap on Euler's identity. Euler's identity is named after the Swiss mathematician Leonhard Euler. Euler's identity is a special case of Euler's formula, which states that for any real number x, e to the power ix equal cos x plus I sin x, where the inputs of the trigonometric functions sine and cosine are given in radians. In particular, when x equal pi, e to the power I pi equal cos pi plus I sin pi. I here refer to the imaginary axis, where sometimes I is also equal to j. Beside trigonometric Fourier series, another form of Fourier series is by replacing each of the sine and cosine terms in equation 0 by their exponential equivalents using Euler's identity, where we have the equation below. If we rearranging, we will have the equation as given in the slide. The equivalence of the trigonometric and exponential Fourier series. The trigonometric Fourier series is given in this equation, and the exponential Fourier series is given in the next equation. If we equivalence these two equations, this begs the question of how the Cn terms are related to the An and Bn term. Likewise, if we consider only those parts of the signal that oscillate once in a period of t seconds, we get A1 cos omega t plus B1 sin omega t equal C minus 1 E minus j omega t plus C1 E j omega t. And for two oscillations in t second, we get the next one. And in general, n equal to n, we have the next equation. If we define an as a new complex number, a naught equal to a naught, an equal 1 over 2 bracket an minus j bn, where a minus n equal 1 over 2 bracket an plus j bn. And if we rewrite the equation, we have the exponential Fourier series as shown in this equation. The evaluation integral to determine coefficient an is 1 over t integral 0 to t ft e minus j n omega t dt. Next, let us revisit example 1 by using exponential Fourier series. Using the equation for an, we have an equal 1 over 2 pi times integral minus pi to 0 minus 10 e minus j n omega t d omega t plus integral 0 to pi 10 e minus j n omega t d omega t. Finally, we have an equal 10 over minus j pi times e to the power minus j n omega t minus e to the power 0, substituting e minus j n pi equal cos n pi minus j sin n pi. Finally, we have our an equal 10 over minus j n pi times cos n pi minus 1. Simplifying a based on the red box on the top right hand side. So we have our a naught equal to 0 for n equal to even, and a n equal minus j 20 over n pi for n equal to odd. For negative values of n, a not equal to 0 and a n equal to 0 for n equal even, a n equal j 20 over n pi for n equal to odd. Only odd harmonics are present in the series. Therefore, our exponential Fourier series is as shown in the last equation. The trigonometric Fourier series can be obtained by calculating the sine and cosine coefficients. An equal to an plus a minus n. So therefore we have an equal minus j20 over n pi plus j20 over n pi equal 0. Bn equal j times an plus a minus n. Therefore we have Bn equal 40 over n pi. The Fourier series is equal ft equal summation of n equal to 1 to infinity 40 over n pi sine n omega t, or if we expand, ft equal 40 over pi sine omega t plus 40 over 3 pi sine 3 omega t plus 40 over 5 pi sine 5 omega t plus triple dot. Now, let us proceed with example 2, finding Fourier series using exponential Fourier series. The analytical equation for the waveform is given Vt equal 10 for t minus 1 to 1 and Vt equal to 0 from 1 to 3. Calculating the An, we have 1 over 4 times integral minus 1 to 1 tan e minus j n omega t dt plus integral 1 to 3 0 times e minus j n omega t dt. Working out with the integration, finally, we have an equal j5 over n pi times minus j2 sine n pi divided by 2. Or, if you simplify, an equal 10 over n pi sine n pi over 2. Next, we proceed with further expansion, simplifying an based on the sign identity equation as given in the red box. We have an equal 10 over n pi for n equal to 1, 5 and 9, an equal minus 10 over n pi for n equal to 3, 7, 11 and triple dot. For negative values of n, we have a minus n equal 10 over n pi and a minus n equal minus 10 over n pi respectively for n equal to 1, 5, 9 for the first one and n for equal 3, 7, 11 for the second one. The infinite exponential Fourier series is given as in the equation below. Our next topic is time shift. Certain waveforms can be odd or even depending upon the location of the axis. If we look at figure A, it is an even function. When the vertical axis is shifted to the position of figure B, the signal meets the conditions of an odd function. And next, when the vertical axis is shifted to the position of figure C, the signal is neither odd or even. Therefore, shifting the vertical axis can be conveniently chosen to obtain either odd or even function. Shifting of the horizontal axis may simplify the series representation of the function as well. Figure A is neither odd or even function. Shifting the horizontal axis to figure B result in odd function. Hence, the series will contain sine terms and constant term. The constant is determined from the original waveform before shifting the axis. Now let us revisit example 3. If we can recall, example 3 is a sawtooth waveform as shown in the figure. The fundamentals for the signal are ft equal 5 over pi omega t for omega t from 0 to 2 pi. The periodic equation is ft equal ft plus 2 pi. We have calculated A naught and the value is 5. Finding the coefficient an using the equation, we have an equal 1 over pi integral 0 to 2 pi 5 over pi omega t cos n omega t d omega t. Next, we proceed with integration by part. Finally, we have our an equal 0. Next, we proceed with determine the coefficient bn using the formula, and we have to do the integration by part. Finally, our bn is minus 10 over n pi. The Fourier series obtained will be ft equal 5 plus summation of n equal to 1 to infinity minus 10 over n pi sine n omega t, where we have our dc term calculated before the time shifting. If we expand the equation, our Fourier series will be as shown in the last equation. Now let us look the same example using time shifting. The function can be made odd by shifting the horizontal axis. The wave is now an odd function as in figure on the right. For odd function, Bn has to be evaluated, but series should contain dc term and sine terms. Based on the figure, we now have the new analytical equation where ft equal 5 over pi omega t minus 5 for omega t from 0 to 2 pi. Putting the new equation ft into our bn coefficient formula, we have bn equal 1 over pi integral of 0 to 2 pi 5 over pi omega t minus 5 sine n omega t d omega t, and we have to do integration by parts. Proceed with the integration by part. Finally, our bn is minus 10 over n pi, and the Fourier series obtained is equal ft equal 5 plus summation of n equal to 1 to infinity minus n over n pi sine n omega t. And if we do the Fourier series expansion, we will get the same equation as before. In the next PowerPoint, we will look at frequency spectrum. Thank you.